Hi class, this video is ultimately going to introduce you to how to do a repeated measures ANOVA or within subjects ANOVA. But we're going to start with between subjects. That way you can see the comparison between the between subjects ANOVA and the within subjects ANOVA. And you can see one of the benefits in regards to the increase in power and how that changes the outcome. So here we see the setup for a between subjects ANOVA, and we can see that we have a single line with the type of cookie that individuals are eating, and in this case individuals are eating original Oreos, double stuffed Oreos, or golden Oreos, and then we're having them rate how much they enjoy eating the cookie. So some of this has already been filled in because we've already covered between subjects. So K is our number of groups. In this case we have 3 groups because we have 3 types of cookies. So you can look here and see that we have 1, 2, and 3, with 1 being original, 2 being double, and 3 being golden. And you can also see that organization here so that you know what those numbers mean if you need to for reference. We have the number of individuals who ate original cookies, the number of individuals who ate double stuffed cookies, the number of individuals who ate golden. Because this was randomly assigned, individuals were randomly assigned by condition, we end up with the same number of individuals in each condition. And then we have a total number of individuals, so a large N, capital N, of 102. And that's just 34 plus 34 plus 34. So we can get these by using count and count ifs, and you should be familiar with each of these formulas as we've already previously used them to some degree. This format may be a little bit new to you. What this is saying is count if, and then it's giving it 2 conditions. That's what the S is saying, right? So there's 2 conditions here, and you can actually do it with more than 2. So if there is a value in B2 through B101, so if you do less than and greater than together, it just says, is there a number in this cell? And A2 through A103 is 1, then it's going to count it. So basically, if there is some value in this cell, and this is a 1, then this row gets counted. However, this row would not be counted because there is a value in B36, but the value in A36 is a 2. So we have to meet both of these conditions. A2 through A103 has to be a 1, and the corresponding B cell, so B2 or B3, depending on what row we're on, has to have some value in it. And then these are each the same, except now we're changing what is in A. So we still need a value in the B column on each row, and now we're looking to see if A2 through A103 is a 2, or if A2 through A103 is a 3. And that will give us the number of individuals who ate double stuffed Oreos when it's 2, and the number of individuals who ate golden Oreos when it's a 3. For our degrees of freedom between, that is the number of groups, or K minus 1. So H2 is 3, 3 minus 1 is 2. Degrees of freedom within is N minus K, so we have big N of 102 minus K, K being 3, and so we end up with 99 degrees of freedom within. That allows us to select the correct critical value, and in an earlier video I already showed you how to use the table in order to find the critical value. Our grand mean, this is the easiest one. This is really what we've been doing the whole time. We just average B2 through B103. So every individual's rating of the cookie gets averaged together. For the mean of group 1, the mean original, now we have to do average if, and we have to say average if A2 through A103 is a 1, then I want you to average whatever is on the corresponding B column. So if A2 is a 1, which in this case it is, then I want you to include the value at B2, 18, in your average. And I want you to go through this entire range and do that. So what we end up having happen is it does the average of everything from B2 to B35, because we can see that at B36, that's where the 2's start, because I've organized these by the type of cookie that the individuals were eating. So if you wanted to check, is this doing what I think that it's doing, or is this doing what it's supposed to do, I could then go and just say, well, give me the average of B2 to B35. If this formula is doing what it should be doing, then when I average B2 to B35, I should get the same answer. I should get 17.32353. And so you can check that you're using the formulas correctly that way. With the mean for group 2, the mean for the individuals that are eating double stuffed Oreos, we see that we again say, looking at A2 through A103, is the value 2, that's the value for the individuals eating double stuffed Oreos. If it is, then whatever is in the corresponding B row, I want you to include that in the average. So we should end up with the average of B36 to B69. Now sometimes data is not easily organized, or you're organizing on several factors, and so these formulas, these functions that we're using, can be helpful. If you're looking at it and you're like, well, why don't I just say average B2 or B36 to B69, you could in this data, but not all data is so orderly, and so these functions can be helpful at that point. Alright, so now we have the averages. Most of that should be familiar to you. And now we're going to get the sum of squares between. And so sum of squares between is going to be the sum of the squared deviations between. And by squared deviations between, what we're really saying is, what is the difference between the group mean, in this case the group mean for the individuals who ate the original Oreos, minus the grand mean, the mean for all Oreo ratings. And we're then going to square that. Now you could do this simple formula. If you do that though, when you get to group 2, you have to change the formula so that you look at the correct mean. So now we say, what is the difference between the mean for group 2, the individuals who ate double stuff, minus the grand mean, and I have to do that for everybody in group 2. To avoid having to write 3 different formulas where I subtract group 1 from the grand mean, and then group 2 I subtract the grand mean, and then for group 3 I subtract the grand mean, I can write one function. It is a little more complicated, but again, this helps you to develop your Excel skills. So if you're still like, no, I just figured out what I was doing before, feel free to use this simpler formula. You'll just have to remember that I'm going to subtract the mean for group 1, I'm going to take that and subtract the grand mean from it. And then when I get to where group 2 starts, I'm going to change the formula at that point so that I have the mean for group 2, subtract the grand mean, and then when I get to where group 3 starts, I'm going to have the mean for group 3, if you're looking here, H12 minus H9. And again, in all cases, I'm going to square that difference, so I get the square deviations. However, if you're feeling confident, if you want to develop your Excel skills a little bit more, what we can do is say if A2 is a 1, right? So if you're in group 1, then, and this is basically the function that we just saw, if A2 is 1, then take the mean for group 1, the mean for the individuals who ate the original Oreos, subtract the grand mean, and square it. If that's not true though, right, if it's false, then go on and do this second thing, or check this second thing. See if A2 is a 2. If A2 is a 2, then take the mean for group 2, subtract the grand mean, square it. And if that's still not true, move to this third option where we see, is A2 a 3? Well, if it's a 3, then take the mean for group 3, right, 15.11765, subtract the grand mean from it, take that difference, square it. Now, if none of those things are true, right, those should be all of our options. If none of those things are true, put a check in here because either the data is missing completely or some group that we didn't know about. Maybe there was a fourth type of Oreo. Maybe somebody ate a mint Oreo and we didn't realize there were 4 groups. This just gives us a check. So if for some reason there's data that we didn't anticipate, then put this in there so that way I can quickly go, oh, I need to check that. I need to see that. So I'm going to use this formula since I already went through all the trouble of writing it out, and I can just drag that down. So what you see is that for everybody in group 3, they all have the same squared deviation between, right? Because it's the deviation between this group and the grand mean. Well, everybody in group 3, everybody that ate that type of Oreo, their mean is all the same. Group 2, similarly, different from group 3 because their mean is different from group 3. But for everybody within that group, they all have the same mean. So their squared deviation from the grand mean will be the same. And then finally, we see that for group 1, their squared deviation between the deviation from the grand mean is also the same. Again, because their mean is the same. And you can see that this is the smallest value all of them. And we know that makes sense because their mean is the closest to the grand mean. Their mean is 17.32353. The grand mean is 17.43137. It makes sense that they would have the smallest, and we should see that these two are relatively similar because one is basically 2.5 points above and the other is basically 2.5 points below. And they are a little bit different, but as you can see, one is 5.86 and the other one is 5.35. They are similar to each other because the difference between 19.85 and 17.43 is similar to the difference between 17.43 and 15.11 or 12 if we're rounding. Alright, so that gives us squared deviations between. Now we can add those to get the sum. So we're going to say sum C2, 2C103, and we see that our sum of squares between the variability attributed to the difference between these means is 381.78, or the squared variability. Now we have sum of squares within. With within, the question is, how far is an individual score from the mean of that group? So before, between was how far is this group mean from the grand mean, and how far is this group mean from the grand mean. Now the question is, how far is this individual score from the appropriate group mean, and then the next individual score from the appropriate group mean, and then when we get to group 2, how far is this individual score from its appropriate group mean, which would be the mean for group 2, the double. And then when we get down to 3, how far is each individual score from this group mean. So again, we could go, well, here I simply need to take the individual score B37, subtract the appropriate group mean. This is group 2, so I would subtract H11, subtract 19.85294. And then when I get to group 3, I would say, we'll take 8B71, subtract H12, because that's the mean for group 3. I could, though, write a similar statement where I say, well, if A2 is a 1, then take B2 and subtract H10. But if A2 is not a 1, then keep going and check and see if it's a 2. If it's a 2, then you should subtract H11. If that's not true, check the next thing. Is it a 3? If it's a 3, then you should subtract the mean for group 3, which is at H12. And if none of those things are true, again, maybe we didn't fully account for all possible outcomes here. Maybe there's another group. Maybe there's something that we didn't account for. We should check that. So I'm just going to use that one, and I'm going to drag it down. And then I can sum those squared deviations. And that gives me sum of squares within. So this is the variability that I can't account for in my model. We often refer to it as error. Maybe it's attributable to something else, so maybe it's not truly error. However, within my model, it is variance that I can't account for. So the sum of squares total should equal 381.7843 plus 3311.235. Now this is actually the easiest one to compute. In fact, this is basically what you've been computing the whole time in earlier independent samples, designs, those types of things, because it's just how far is each individual from the grand mean. Well, before we really only had one mean, like in a one sample t-test, we have the sample mean, and we're like, how far is this individual from the sample mean in order to get that variability? So this is how far is this individual score of 18 from the grand mean. The grand mean is the same for everybody, so this is the simplest formula actually, where I just subtract H9. I do have the dollar sign in there telling it to stay static on H9. The grand mean is the mean for everybody. I don't want it to move as I drag down this column. And then I can add that together. Again, if I've done this correctly, it should be that between plus within gives me total. So when I sum E2 to E103, if everything is done correctly, I should get 3,693.02. So this gives us a quick check. So I'm going to get rid of that, and I'm going to say, all right, check and see E2 to E103, sum that. I still end up with 3,693.02. So if I add these two scores together, I still get the total, but it's good to do it this way and then have these two scores, because then I can double check. If I just add between plus within, assuming that it's the total, that assumes that I've done everything correctly. It takes away my ability to check that I've done it correctly. For mean squares between, it is simply sum of squares between divided by degrees of freedom between. And for mean squares within, it is sum of squares within divided by degrees of freedom within. And now that I have those, I can take mean squares between, divide by mean squares within. So basically, my effect, the variability that's due to the between group differences, divided by my error, divided by the variability that I haven't accounted for in this model, and I find that my F obtained is 5.707333. I can also get eta squared, which is going to be the sum of squares between, so my effect, divided by my total variability, so H15, so sum of squares total. And I find that eta squared, an effect size, so we've talked about effect sizes before, we use Cohen's d. Eta squared is another effect size measure, is 0.10338. And your book introduces what's a small effect, what's a large effect, and so you can look there in order to kind of categorize or classify this effect. You would find that it's in fact a small effect. Alright, so we've done this with the between subjects design. And remember, the big thing is the formatting of the data. I have cookie type, and then I have the rating. This represents one person. Each person ate one cookie with the between subjects, and I'm comparing the people who ate the regular or the original Oreos to another group, a different set of 34 people who ate double stuffed Oreos, and another set of 34 people who ate the golden Oreos, and so I have 102 total individuals. Now let's say that I don't have 102 total individuals. Well, one way that I can deal with a limited number of individuals is with a within subjects design. So this data is actually identical if you look at these scores and compare them to group 1 from the between subjects, you'll find that the scores are identical. And if you compare these to group 2, you'll find that they're identical, and these to group 3, you'll find that they match. The difference here is I have 3 Oreo ratings on a row because person 1 came in and being lucky, instead of only eating 1 Oreo, they ate 3. Although they had to eat golden, and golden are disgusting. I don't know why they ever made them. Double are amazing. Original are good as long as you have some milk. But double, that's really where it's at. So when we look at this, we see that we have this person came in, we'll call him Sam, right? Sam, who was person number 1, came in, ate an original Oreo, scored it, ate a double stuff, scored it, ate a golden, scored it. Now this can be problematic from a design standpoint because maybe Sam is now comparing original to the double whenever he goes to eat the double, and he goes, well, double is better. I got to score it higher. I gave the first one an 18, right? Because of that, there are problems with this design. It doesn't work with everything. And I'll let Dr. Bird talk more about that in experimental. But at the same time, if Sam just absolutely hates cookies, hates sweets, hates Oreos, Sam's scores on all 3 types of Oreos would then be low. So this allows me to ignore that individual variability the same way that when we compared the dependent samples t-test to the independent samples t-test, I ended up with some additional power because that individual variability, do you like Oreos, do you not like Oreos, doesn't end up getting wrapped into my error term. It's going to end up going into this sum of squares subject or sum of squares participant. And so it's going to end up going into that, and then I'm going to remove it from the error term. So it's not part of the effect, but it's also not part of the error. It is another factor that I have accounted for. It's another source of variability that I've accounted for. And if I account for it, it doesn't count as error anymore. And in fact, it really wasn't error to begin with. It just was a source of variability that in the within subjects design I couldn't account for because I didn't have a method of accounting for it. So you can see here that to save some time, I've already calculated the N. It's just the number of individuals who are eating the Oreos, 33. And I think it actually should be 35. Oh, Sam now, because he's not a number anymore, isn't being counted. We're going to switch this back. So there's 34 individuals. K is still 3. That is now the number of conditions or the number of times. We know that there are 3. And there are a number of formulas you could use, but for the moment I'm just going to put in the 3. The number of conditions, degrees of freedom conditions, is K minus 1 still. Degrees of freedom error is now N minus 1, so 34 minus 1 is 33, times K minus 1, so 33 times 2, which gives us 66. So we have 2 and 66 degrees of freedom. Our grand mean, still just the average of all the scores. So we have 34 ratings by 3 different types of cookie. And so our grand mean is going to be the average for all 102 tastings. So all 3 cookies for all 34 individuals. The mean for original is going to be the average of this first group, the column B, because those are the scores for the original Oreos. The mean for double is going to be the average for column C, because that's where the double scores are. And then the mean for golden is going to be the average for column D. So again, kind of rushing that ahead, but I think those are all formulas that you should be familiar with now. If not, I would recommend going back, doing some of the older practice problems, because as I've mentioned before, I kind of start assuming that you know some of this so that I can focus on the later parts. So for our sum of squares total, this is going to be the sum of x minus the grand mean. And by x, we mean the score for each individual. So the square deviations of the original minus the grand mean for the first person, and the double minus the grand mean for the first person, and the golden minus the grand mean for the first person. So 18 minus 17.43137, square that, add 25 minus 17.43137, square that, and then add the square of 0 minus 17.4317. And so I do that for the first person, I do it for the second person, I do it for the third person. So I have to do that for all scores. So that's what's going on over here with square deviation original, double, golden, is the individual score minus the grand mean for original, individual score minus the grand mean for double, and then individual score minus the grand mean for golden. So once I've created those, I then tell it to do that for all peoples. And then I can go in and say, now sum those square deviations from F2 to H35. And I could type it out. As you see here, I can also start it and then just highlight the cells that are of interest. Now for condition, you can see here that I'm going to take n is at G2. I'm going to multiply it by the sum of the mean by condition minus the grand mean. So the mean for this condition, right, for B2, right, original, minus the grand mean, and then the double minus the grand mean, and then the golden minus the grand mean, and then I can just multiply by the number of people. So that's basically like doing it by each line, except I don't actually have to create a new column for each individual person for these, because I'd have to create 3 more columns. So we're going to say, all right, equals n to account for the number of individuals. So instead of having to do it by each line, we just multiply by the number of lines, or the number of rows, and then sum, and we are going to say original minus the grand mean. We do need to put that in parentheses so it does that subtraction first. Then we can square it. And then we're going to say double minus the grand mean. And then square that. And then we will say golden minus the grand mean. And then square that. And then we are going to sum those values. There we go. So we have now the sum of squares for condition. Now the sum of squares for subject. For each subject we have 3 scores. So we have to account for the number of scores by subject. That's where the k comes in, why we multiply by k. And so we're interested for each person, for each individual, what is their mean minus the grand mean? So how far is this person? That's how we account for, do they like Oreos or not? If the person likes Oreos, their mean should be a little higher than the grand mean. If the person hates Oreos, their mean should be a little lower than the grand mean. And we want to account for that variability so that we can partial it out, so that we can remove it from the error term. So now we're going to say equals k, which is at L3, times the sum of I2 through I35. And what we're going to do within I2 to I35 is we're simply going to take the individual person's mean and we're going to subtract the grand mean. So I want to tell it to stay stationary because, again, the grand mean is the grand mean for everyone that's in this data. The individual mean is simply the average of this person's scores, so 18 plus 25 plus 0, and then divide by 3, the number of scores. So you can use the average formula, average B2 to D2. And then I'm going to drag this down so we have the averages for everyone. And then once I get those averages, I can then drag this down and see how far is this person from the grand mean and then the next person. So these first couple of individuals don't seem to like Oreos quite as much. And some of the individuals, if we look, like this individual likes Oreos more than average. So their average is 20.67 if we're rounding. The grand mean is 17.43. So they deviate from the grand mean, particularly in a positive direction. But of course, we're squaring it. Thus, we're ignoring whether they're above or below the grand mean for the moment. Then, those scores get summed together and pulled over for the sum of squares subject. And then the last thing we're going to do is get the sum of squares error. Well, before, error was the total minus between, if we're thinking about a between subjects design. Now, it's going to be total minus condition, which is the grouping variable basically, right? We have the 3 different conditions, the 3 types of Oreos, and we also subtract the subjects. So we should end up with a smaller error term. Because we have a smaller error term, we should end up with a larger overall F obtained. So when we do mean squares condition, it's still sum of squares condition, which is at L11, divided by degrees of freedom condition, which is at L4. Mean squares error is L13, which is the sum of squares error, divided by degrees of freedom error. And then our F obtained is still mean squares condition divided by mean squares error. So the effect divided by the error. But again, now the error term does not include the individual variability. We've removed it. We've partialed it out. So if I look here, my F obtained is 8.27667. In the between, my F obtained was 5.7073. Well, mean squares between was 190.8922. Here, mean squares condition, right, type of Oreo, is 190.8922. So the effect is still identical. The difference is this error term is smaller because I have partialed out, subtracted the individual variability, the variability that's due to just broadly, do I like sweets, do I like Oreos, do I like cookies? Well, I'm not interested in that. I'm really interested in between these 3 types of cookies, which one do you like more? Is there a difference? And so I'm not interested in overall, do you like cookies or do you not like cookies? I can remove that. This makes my error term smaller compared to the between subjects design. And then that ultimately means that my F obtained in the between is smaller because my denominator is larger, and my F obtained is then larger comparatively in the within subjects because my denominator, my error term, is smaller. So gives you a comparison of within and between subjects. Also shows you how to do the within subjects ANOVA.